Alright, so this is Griffiths Quantum Mechanics, problem 2.10. And let's see, it's a three-part problem. The first part we have is to find, or to construct the I guess this would be the third state, energy eigenstate of the harmonic oscillator. Right, so you have side 0, side 1, and now we're on the side 2. All right, and I'm going to, I'm going to cheat a little bit and use, he already constructed the first excited state for us in example 2.4, okay? So, so I'll just write that out and we'll go from there. So I will go back through example 2.4 and reconstruct it. Okay. So what we have here is a m omega over the pi h bar to the 1/4 power here. And then we have a 2m omega over h bar under a square root. And then we have an x, e to the minus m omega over 2h bar x squared. All right. So here's our psi 1. And we're just going to use the construction operator, or one of our ladder operators. You can find this, looks like equation 2.47. All right, so I'll just go ahead and write that out for us real quick. This is it defined. All right, so 2h bar m omega, and this is under a square root down here. And then for the construction operator, we have a minus sign right here. I p plus m omega x, like this. Okay. All right, so when we turn this into actual, I guess, operator, we end up with this 2h bar m omega, and then in here we have a minus h bar, and then derivative with respect to x plus m omega x. Okay, right? Because p is just equal to h bar over I times derivative with respect to x position. Okay, so now we have this, and we can get to work on this the second excited state that we want here. All right, and there's also a normalization factor, right? But if we look in sort of equation 2.67, it tells us that that is 1 over, in this case, it's the square root of 2 factorial, okay? So 1 over, you know, if this were 3, there'd be a 3 here. So you can look at equation 2.67. All right, so we'll just dive in here. So we'll start bringing the constants out front, starting with this one, m omega pi h bar, 1/4 power. It'll be a miracle if we get through this without me making a mistake somewhere in all of this. And then we have this one, which is 1 over 2h bar m omega under a square root. Okay, and then I'm just going to start down on the new line, so we have space. The minus h bar d by dx plus m omega x. This is what's acting on x from up here. X e to the minus m omega x squared over 2 h bar. Okay, and then so I think we're good to go. Okay, so we'll just be sort of concentrating on this bottom piece for a little bit. So that's what we have to. The rest is all just a bunch of constants. All right. So I have to remember to put everything back together when we're done. And so I'm going to start with the second term because that's easy, right? So m omega x and the x squared here, e to the minus m omega x squared over 2 h bar. Okay, now on to the fun part. So we have a minus h bar, and now we have to take the derivative of this. So we'll use the product rule. So first I'm going to take derivative with respect to x. So basically the x just goes away. We have an e to the minus m omega x squared over 2 h bar. Okay, now we have to take derivative with respect to this. And our minus sign is out here, so we'll just use a plus. Okay, so we have, first we'll bring the constants down, minus m omega over 2 h bar. Then using the chain rule, we have to take the derivative of the x squared, so we have a 2x. And then we just have our exponential. So you can, this exponential is just up here. This is really tiny, it's hard to read, but okay. So I think we may have this all set up for us here. Okay, I think the units look good so far, so I think okay. All right, so now let's, we have all of this junk right here that actually goes in this place, and we have all these constants out front. So this is going to be a little messy. So the factorial of 2 is just 2, so we just have a 1 over square root of 2 there. We have our m omega pi h bar to the 1/4 power. See if we can simplify any of this down a little bit. What do we have here? This square root and this square root, we can get rid of a 2, and m, and then omega, and then we have a square root of h bar on the bottom and a square root of h bar on the bottom, so that's just going to give us a 1 over h bar, so that's nice. All right, now we're sticking in this big guy down here. So we have, I'm going to factor out the exponential because it's a mess. I'm going to draw a line here so we can kind of keep these guys separate. All right, now we'll have the m omega x squared minus an h bar, and then minus, right, this minus h bar is going to get multiplied in to this right here. I'm going to cancel these 2's, and we can even cancel this h bar and the minus. So we have a plus, let me just see here. So we have a minus, well, let's just write it out, why not? Minus m omega over h bar. And there's an x here too. maybe our units didn't work out. Let's cross our fingers. Go back and look at my notes real quick. All right, I'm gonna double check this part. Okay, so I found my mistake. All right, the units did not work out. Which anyone? Okay, so let's see. The problem was when I did this product rule up here. I forgot to leave the x on for the second part, right? There's an extra x right here. So this is actually an x squared right here. Okay, so when we come down here and simplify this, we have 1 over square root of 2 rm omega over pi h bar, again, to the 1/4 power. I'll deal with this h bar in a second. E to the minus m omega x squared over 2 h bar. Okay, draw one of our little lines to keep everything separate. Okay, so we have, when we divide by h bar, so first of all, this will cancel with this, and the minus sign is going to cancel with that. So we have 2 of these m omega x squared parts. So 2m omega x squared, and then we're dividing by h bar, and then we have this minus h bar, which divided by h bar is just a minus 1. Okay, so here we have the part A, right? This is the wave vector that he asked us to construct. I'm going to write it out here so it's more pretty. 1 over square root of 2 m omega over pi h bar. And then, why not just bring the exponent to the end? 2m omega x squared over h bar minus 1. And then our exponent, e to the minus m omega x squared over 2h bar. So here we go. So, here's our answer to part A. Now, we're going to talk a little bit about, it says sketch the ground state and the first and second excited states. So, well, I mean, you've seen the pictures in the book probably. Let's see, it looks like figure 2.7. You have some nice pictures of them there, so I mean, we know kind of what we're looking at. But basically, with the ground state, it's just a Gaussian distribution. So if we go back, I'll just I won't worry about the constants here for a second. So ground state is proportional to just an e to the minus. I'll just use a k for a constant here, x squared. Okay. First excited state is proportional to, so neglecting all the normalization and everything, we just have an x out front, e to the minus kx squared, and our second one, excited state, which we just found, all of this is constants. So what it looks like here is we have something proportional to an x squared, e to the minus kx squared, but then we have minus some other constant, just call it a, e to the minus kx squared. Okay. So the third one here is a little bit complicated because we have this minus 1 thing in here. But we can go ahead and sketch these guys. So the ground state is just the form of a Gaussian. Look it up, anything to the minus something x squared, right? You just get a nice bell curve, something like that. Okay, the first excited state is this exact same thing, the ground state, but you multiply it by x. So x looks like this, right? So it has to go to 0 here in the middle, because when x equals 0, it'll bring the whole thing down to 0. And then x is positive on this side and negative on this side. So when you multiply those two together, you'll get something. So negative on this side, right? And by the way, an exponential is going to kill any power. Alright, so this is just a power of 1, it'll kill it nicely. Okay. So it kills it. So even when x goes off to infinity, the exponential goes off to 0 much, much faster. And this will go to 0 at infinity, which is good because we want it to be normalizable. And so again, 0 in the middle, it's going to, you know, anyway, basically that's what it's going to look like. All right. So, oops. So here's our first excited state. Now we need to look at our second one here. And so let's see if we have enough room here. We'll just, as long as we keep in mind what we're doing, we shouldn't get too confused. So in each case, we have a one of these exponential curves, which I'm having trouble drawing, or one of these Gaussian curves, right? In the first case, it's going to, rather than be multiplied by a line, it's going to be multiplied by a parabola. And it looks like, you know, if you actually draw this to scale and everything, it's probably, because this looks like it's shooting off to infinity much faster. So maybe I shouldn't draw it that way. But again, the exponential is going to kill. It doesn't matter if it's x to the 200. The exponential will still kill it. So it'll still go to 0 at infinity. It's still normalizable. So this is the first part right here, okay? And the second part is just going to be one of these, except flipped upside down. So this is all really, I guess, a convoluted way to draw this. One sec. Handle the phone. All right, telemarketers. Okay. We have, all right, so again, okay, so let's just look at the point at 0 here real quick. Because of this right here, this part will go to 0, and this will be just its normal value, except we have this minus sign right here. So basically we'll get a negative value at 0. And we know it has to go to 0 off at infinity. So let's see. You know, and the number of nodes, or the number of places where it crosses 0, depends on how much energy the wave function has, right? So the ground state has 0 nodes. It doesn't cross the 0 axis ever, right? The wave function never goes to 0. The first excited state has 1 node. The second excited state will have 2 nodes. So we know it has to cross this horizontal axis at 2 places, right? And we know it's down here. And we know it goes to 0 at the ends. And so I'm sure there's more sophisticated ways of figuring out exactly how high it goes and everything, but we're just sketching. Who cares? So basically, it will cross and then go off to 0, right? And you can look in the book, figure 2.27 or whatever that was, to see much better pictures of this. All right, but the real reason we want to sketch these things is because the last part of the problem is check the orthogonality of these things by explicit integration. And if you exploit the evenness and the oddness of the functions, there's really only one integral left to do. So what he's saying basically is that this one here, this half is less than 0, and this half is greater than 0, and everything is symmetric about this line for these other two. I guess I should draw that on. So this is a mirror image of this is a mirror image of this, and this one would be a mirror image except there's one minus sign. So when we do our integration, any even function multiplied by an odd function when we integrate by a symmetric, in this case minus infinity to infinity, or even if we were to go from -1 to 1, as long as we're symmetric about this vertical axis here, the integrals will go to 0. So the long story short is that we can do 2 integrals right off the bat based on just this symmetry of it. Okay, and that's just when we mix an even function with an odd function. So this one is going to equal 0, and also this one. All right, because here we have this odd function, so even and odd and even, these two will go to 0. All right, so the one we're left to do is the 2 even functions. We want to check orthogonality for the ground state and the second excited state. So here we go into a bunch more messy math. All right, so let's see if I gather our pieces together here. Okay, I never wrote down the ground state explicitly, but like I said, we can find that on equation 2.59. Maybe I did write it down. I don't know. Probably a different problem, actually. Okay. So 2.59 is where we find this. So the ground state, we did this m omega pi h bar thing again to the 1/4 power. That's just the normalization factor, and then e to the minus m omega x squared over 2h bar. Alright, so there's that. Now, here we go. So we are looking at this integral right now. Okay. So, we have this one and this one. So, the first thing we're going to do is combine these two terms. Well, let's write the 1 over square root of 2 quick. And combine these two terms. Pi h bar to the 1/2 power now. Okay. Then we have 2m omega x squared over h bar minus 1 from up here. And then we have 2 of these exponential terms, minus m omega x squared. So instead of over 2h bar now, it's just over h bar. And this is all integrated with respect to dx. All right. Now I'm going to go ahead and ignore the constants for a little bit, because hopefully we'll show that this thing is orthogonal, and the integral will equal 0, so the constants won't matter. So we're just going to focus on this piece right here. Okay, so we'll go ahead and write this out. Bring the constants out front, 2m omega over h bar. And I'm going to split this into two integrals, okay? So one for this term right here, and one for this term right here, minus 1. All right, because this one has the x squared in it, so that's the real kicker. What's the actual difference here? So here's the x squared, and these are all going to be minus infinity to infinity. So x squared e to the minus m omega x squared over h bar dx. Okay, so here's one of them. And then minus this one, just, it doesn't have these constants mixed in. It's just this e to the minus m omega x squared over h bar dx from minus infinity to infinity. All right, so this isn't an equation, I guess. It's just an expression. But if this expression is equal to 0, then we prove that our ground state wave function is orthogonal to our second excited state right here. Okay, so I'm going to cop out and not do find all these Gaussian integrals explicitly. Basically, with these, I always just look them up in a table. So you can go on Wolfram Math World or Wikipedia or whatever, and find Gaussian integrals like crazy. So I went and I looked, and so this integral of e to the minus, we'll just use a constant a, x squared dx is equal to pi over a under a square root, okay? And this integral, minus infinity to infinity, of x squared e to the minus a x squared dx is equal to 1 over 2a, and then pi over a under a square root again. All right, so now that we took the trouble to look these up, we just need to figure out what a is and everything. Everything should work out nicely. So in both cases, we have the same dealio up in the exponent, and so a in both cases is equal to m omega over h bar. Could use alpha for this, and a lot of people do. Okay. Now we look at our expression right here. So looking at this first part first, we have this constant in front, 2m omega over h bar right here. Now we are going to, you see that this is the integral we want to look at for this one, which is just 1 over 2a, and again, a is this. So what we have is, we'll have a 2 on the bottom, an m omega, and an h bar, like that. And then we have a pi over a. So pi h bar over m omega over a square root. All right, and this is beautiful because these completely divide out, right? We get just this right here. Okay, for that's just for this first part. Now for the second part, I'll just continue off the side here. So we have a minus sign. Now we're looking at just this equation right here, which is just pi over a, which we know is going to work out because that's pi h bar over m omega square root. All right, so this this is the same as what's in the box, and we get the big fat 0 for this expression, right? We get two of the same thing. We get this square root of pi over a for this one, square root of pi over a for this one. This expression goes to 0, which tells us, because this was, we just got this from, we just took out the constants and got this, right? Basically, it tells us that this term right here is equal to 0. Well, once we throw in this, okay? So this term is equal to 0. That tells us this whole integral is equal to 0, which tells us that this integral we were doing right here is equal to 0. So let me highlight the final result that we get right here. Okay. Basically, taking the inner product of the ground state of the quantum harmonic oscillator with the second excited state will give you zeros. These two states are orthogonal. And this just extends on. So I mean, basically we're just showing that we're just showing explicitly these first few, but all of these wave functions for the harmonic oscillator are orthogonal. So either by the even-odd argument you can make, or by doing out these huge integrals. Well, I'm sure some people will just say these are easy integrals, but you can show that the whole set is orthogonal.